Welcome to first actual theory lunch in 2 years. We have team here to talk about algorithmic thresholds for refuting random polynomial systems. Here you go.
Hi everyone, I'm Tim, and I'll be talking about our paper, Algorithmic Thresholds for Refuting Random Polynomial Systems. And this is joint work with my advisor, Pravesh. So let's jump right in. So suppose we're given input m polynomial equations, P1 to Pm, and each equation is Pi of x equals Bi, like this. And suppose each Pi is a homogeneous polynomial of degree capital D, and its coefficients are sampled from the Gaussian distribution. And suppose the Bi's are also IID Gaussians. So this is the input polynomial system that we're given. So first, it's quite easy to see that when m is larger than n, this system of equations has no solution. And here's why. There's this Bezo's theorem that states that the number of common zeros for n generic degree D polynomials is at most d to the n. And this number is it's not important. It's important that it's finite. So let's say we have n polynomial equations, and now we add the next one. The probability that this new polynomial is zero at any of these finitely many points has to be zero because our polynomial is random. So this shows that when m is larger than n, there is no feasible solution for this system. And we call this the information theoretic threshold. So our question is, what's the smallest m such that we can efficiently find refutation? When I say refutation, I mean certify that it's unsatisfiable. And we call this m the algorithmic threshold. Okay, so in this talk, I'll focus on upper and lower bounds of this algorithmic threshold for refuting. So let me first explain what are refutation algorithms. So suppose we're given a system of equations, and a refutation algorithm is an algorithm that either correctly outputs infeasible or returns don't know. So here, correctly outputs is important because when it outputs infeasible, it has to be correct. Yeah, and so it means that if it outputs infeasible, this is a proof that the input system is unsatisfiable. So what we want is an efficient refutation algorithm such that, first, of course, it takes in the input system P of x equals Bi as input. And with high probability over the randomness of the input equations, it correctly outputs infeasible. So notice that you cannot always output infeasible, even though with high probability, the input equations are actually infeasible. You cannot always output infeasible because that's not a valid refutation algorithm. And so I want to just say that the notion of refutation is not new. It's very well studied in various areas, like in proof systems, in random CSPs. Yeah. Okay. So let's talk about some motivations of why we're studying this problem. First, in algebraic geometry, researchers have been very interested in this random polynomial systems and their common zeros. It's been very well studied. So it's a natural problem for us to study. In combinatorial optimization, you can think of this our random system as a dense analog of random CSP refutation. So the normal CSP refutation that we're more familiar with, like random max cut or 3-sat, etc., they're sparse in the sense that each polynomial has just a constant number of monomials. But here our polynomial is dense, where it has like n squared, or like all the monomials are present. So it's a natural dense analog. And in statistical learning, our problem is actually very closely related to the matrix sensing problem, and where the measurements are Gaussian measurements. And last but not least, in cryptography, there's recently been candidate PRGs based on random polynomial systems. So this is also another reason why we're studying this problem. So hopefully these, I've convinced you that this is an interesting problem to solve. Okay, so for this talk, I'll mainly restrict the case to when the PIs are degree 2, so they're quadratic polynomials, just for simplicity. So let's make a first observation. When m is larger than n times n plus 1 over 2, this problem is easy. And we call this the linearization threshold. Why is that? We use this linearization trick. So for each xij, we just replace it by a variable yij. And then we just run Gaussian elimination. So when m is larger than this n squared over 2, roughly n squared over 2, Gaussian elimination will show you that this is infeasible with high probability. So our question is, can we beat this in polynomial time or in sub-exponential time? Can we lower this m required to refute this system? So here's a diagram. We know that below n is satisfiable, and above n is unsatisfiable with high probability. Actually, with probability 1 because it's Gaussian. So above n squared over 2, we can do this linearization trick to refute. But what can we do in this region? So let's jump into our results. The short answer is that we can non-trivially beat the linearization trick threshold, by a small factor. So more specifically, for any d, we give an n to the O of d time refutation algorithm that succeeds when m is greater than this order n squared over d. And the algorithm is just the sum of squares algorithm. Here's a diagram. So you can see that there's a natural interpolation between polynomial time and exponential time. So when this d is constant, it's polynomial time, but the threshold is roughly n squared. And as you gradually increase d to order n, the runtime goes from polynomial to exponential time, but the m required goes to n, and this n is the info theoretic threshold. Okay, and now we have some lower bounds. Basically, we want to show that this line is almost optimal, or we give evidence that it's optimal. So we prove that degree d polynomials fail when m is smaller than this threshold, which is the same order as our upper bound. And I'll explain what degree d polynomials fail mean later. This hardness result is in the low degree hardness framework. We show that low degree polynomials cannot distinguish the null model, which is our random polynomial system that we're analyzing, and a planted model, which is a certain distribution that we construct over feasible polynomial systems. So notice that these two, the distinguishing task between these two is actually easier than the refutation problem, because if we can refute, then we can distinguish these two. So on the flip side, if we show that a certain class of algorithms cannot distinguish these two, then we show that these algorithms cannot refute. So here's a crucial point of our paper. The natural planted distribution doesn't work. And I'll go into what the natural planted distribution mean later in the talk. But for this distribution, the solution can be recovered when m is a tilde order of n, which is close to the info theoretic threshold. So yeah, I'll explain this later in the lower bound section. And we also prove some SOS lower bound. And here we restrict to random quadratic polynomials. We show that for degree 2 SOS, there's a sharp threshold at m equals n squared over 4. So this means that with high probability, when m is larger than n squared over 4, roughly, there's a degree 2 SOS refutation. And if it's smaller, then there's no degree 2 SOS refutation. I haven't. Yeah, I haven't defined it, but I will do it later. Yeah. And for degree 4 SOS, we prove that when m is roughly n squared, there's a degree 4 SOS lower bound. So degree 4 SOS cannot refute our input system. And just a comment that this matches the threshold that predicted by the low degree hardness. Yeah, I think I didn't mention that SOS lower bound means that SOS cannot refute the input system. Yeah.
So maybe you're going to hint at this later in your talk, but like I understand what the refutation looks like in the linearization case, right? It's like Gaussian elimination, like the J certificate apply this. But what is it like? Can you give us examples of what this might look like in like these cases? Like what should I think about when I think about these certificates?
Yes. Okay. Yeah. So I guess like you're given any polynomial system, any polynomial constraints, and you can formalize it by SDPs or like these hierarchies of SOS, and you just solve it and see if it's feasible. So if the original system is feasible, then SOS is always feasible, but that's the other way is not true. So SOS might be feasible, but the input is infeasible. So if the SOS thinks that the input system is feasible, then we say that SOS fails. Yeah.
Aren't you going to give something much more simple in terms of the upper bound?
Oh yeah. The upper bound will be simpler. Yes. This is it's like a very high level overview of the results, and I'll dive deeper later. Yeah. Okay, so just a summary. The results above strongly suggest that there's an algorithmic threshold at n squared over d for n to the O of d time algorithms. And our previous results are all stated for quadratic polynomials. Okay, yeah, there's information theoretic gap, information computation gap, sorry. And for more generally for random degree capital D polynomials, the threshold is at n to the d over little d to the capital D minus 1. But for this talk, we'll just assume capital D equals 2. Okay, so now I'll dive deep into our results. Wait, I think it's time for questions. Is there any? Yeah.
Yeah. Okay. So you said like at that one place you had like the sharp threshold at n squared over 4. So that's like when d is 2 or whatever. Okay, degree 2. Oh.
Yes, the degree 2.
But do you have any idea of where is when you have the O of d term in the exponent n to the O of d? Do you have any idea what you expect the sharp threshold to be there? Like what constant you expect on d and the exponent of your algorithm?
Oh, so sorry, n to the O of d. You're referring to, I guess,
along your algorithm.
This right?
Yeah.
Yeah. So that's the runtime required to run the SOS, a degree D SOS.
Yeah.
Yeah.
But like, what kind of like constant are we looking at? Like how good do you think you can get for the threshold? Like where do you think the answer is?
Oh, you mean the constant in the exponent?
Yeah, the constant in the exponent.
Yeah, yeah, for degree SOS, I think you need degree like there into the roughly into the 2D variables, and yeah, I forgot the size of the SDP actually. Pravesh, do you remember?
So there are like 2 degrees here and that might be confusing. So are you talking about like the extension of the result to degree D polynomials, or are you talking about higher degree SOS relaxation?
I think it's about higher degree SOS relaxation.
Is that the question?
Okay, wait, I don't know. Wait, so the little d here.
Yeah.
You can focus on capital D as too.
Yes. And so the exponent here really is like the runtime of the ellipsoid algorithm on the SDP.
Okay, sure.
The SDP relaxation. So
okay, maybe some of that will become clearer like later in the talk.
actually, I won't explain the ellipsoid algorithm because
I mean, I know you won't explain much, but like you'll explain like how you do this.
Or like how
Right.
to decide who the SDP is.
Yeah, exactly.
Okay.
Okay.
Omar has a question in the chat.
Yeah.
It's a bit long. Read it. Could you cover what the Greek?
Wait, should I just
What
say
can
it?
I
Or?
see? Oh, how would some of the usual polynomial proof systems like polynomial calculus, null-silence perform? Ah, okay, good question. Our upper bound is actually null-silence. Okay, let me move this. Can I move this? This is his question. Oh, never mind. Yeah, so our upper bound will actually be null-silence, and null-silence is actually the worst, strictly weaker than sum of squares and polynomial calculus. Yeah, but I won't go explain like what the differences are. Yeah, and is there exponentially long proven to be exponentially long on the average case? Yeah, so our upper bounds are is actually captured by null-silence. Okay. I hope that answers this question.
Maybe you can confirm with Omar.
Yeah. Okay. Yeah, Omar, if you have other questions, just type. Okay. So now I'll dive into some of the details of our results. So first, upper bound. Let's go over some background about proof systems. And here's a toy example. This following system. So is this feasible or infeasible? Okay, I'm just going to tell you it's infeasible. So how do we prove it? We can say, okay, x1 and x2 has to be plus or minus 1. Oh, sorry, 1 over 0. And basically, the first three equations tell you that they both have to be 1, but the fourth equation cannot be satisfied. But is there a way to like algebraically prove that it's infeasible? Here's a way. We can consider linear combinations of the above equations. So the green ones are coefficients of the linear combination, and the red are just the equations that we have. So they sum up to 1. You can verify this easily. So we have a 1 equals 0. We have derived 1 equals 0, which is a contradiction. So this is a refutation. Like this is a refutation that this system is infeasible.
What the intuitive argument you gave before, just so that all of us can follow? Before, like this, syntactic argument, you had like some intuitive argument why the system is unsatisfiable.
Ah, okay, yeah. So the first two equations tell you that x1, x2 has to be either 1 or 0. So, and the second one, basically, sorry, the third one tells you that they're both 1. Otherwise, like 1, 0, 0, 1, 0, 0 won't satisfy the third one. Yeah. This is a simple example I came up with. Yeah. Yeah, but this is like for a computer, this is actually a systematic way to generate refutations or to prove to you that this is infeasible. So more generally, given a system of constraints, polynomial constraints, f1 to fm equals 0, we can derive many more high degree equalities. For example, we can multiply f1 by x1, x2, or any monomial. We can also add these things together. They all have to be 0, right? So any linear combination where the coefficients ai can be polynomials, this has to be 0 as well. And if the max of the summand degree of ai fi is less than d, then this derivation can be captured by the degree d SOS proof system. Okay. So like Omar said, it's hinted, this can actually be captured by the weaker degree d null-silence proof system. But we won't distinguish these two for this talk. So when we say SOS can capture this, what I mean is, given this system, if there exists a1 to am such that this equals 1, then we get 1 equals 0, which is a refutation. And we call this a degree d SOS refutation. And such a refutation, meaning these coefficients, a1 to am, can be computed by degree d SOS in n to the order d time. And I guess this comes back to your question, of the runtime.
Just to confirm, are you defining degree d SOS refutation, or are you claiming that this is the SOS?
I'm claiming this is an SOS refutation, and I like the derivation rules. These are the derivation rules, and these rules are actually captured by the strictly weaker of silent sauce.
Sure.
Yeah. So,
Why do you need SOS? You have inequalities, not inequalities in all of that.
yeah, exactly. So that's why it's actually captured by the null silent sauce. We don't actually add any square polynomials here.
You just greater than SOS.
Yeah, you can think of it that way. Yes.
Also, maybe inherent to your question, another question is like, if I only have equality constraints, could inequalities have a principal constraint? And the answer to that is yes. So it's not in general true that if you only have like equality constraints, then there is no generic reason why you can somehow not gain by what you inequality. You could have, but here apparently it doesn't need.
Yeah, but I'm asking why you need SOS. There should just be a way in the system if you want to actually fix things like that. Hold on.
So you're right, like this kind of derivation that you're defining, they are like a very special case of sum of squares refutation. So you're right, like he doesn't need it, and that's what this null silent purpose is. It's basically this linear system that you propose.
Yeah, exactly. And yeah. Yeah, I guess we state it in the language of SOS because our lower bounds are in terms of SOS. So there's like the upper bound can be captured by a weaker thing, but our lower bound is against SOS. So that's why I guess that's the main reason we state our upper bound results in SOS. But it's actually it should be stated in null silent sauce. Yeah. Okay. Yeah. So another observation. So as we increase D, this proof system just becomes more powerful because you see we have more freedom to choose the coefficients A1 to AM. So it gives us more power to get that one, right? But this is at a cost of increase in runtime. Okay, so anyway, this is just saying that as D increases, this proof system is more powerful, but requires more time. Okay, so back to our problem. Given system Pi of x equals Bi, we showed that the generated ideal at degree D is complete. So what does this mean? This means that for every homogeneous polynomial f of degree D, there are coefficients A1 to AM. These are all degree D-2 polynomials, such that this linear combination of a Pi minus Bi equals f. Okay. So why do we have a refutation given this? Because, so first we pick I to be the first equation, Pi equals Bi, P1 equals B1, and we can derive P1 to the D over 2 equals B1 to the D over 2. And then we just move B1 to the left side, we get this. Now P1 to the D over 2 is a homogeneous degree D polynomial. So and by the completeness of the generated ideal, there exists coefficients A1 to AM such that this equals 1. But like each of these has to be 0. So we get a contradiction. We get a 1 equals 0. Does this make sense?
So what's the quantification on PIs and BIs? Like, are you proving this for all PIs? There exist PIs or random PIs?
Okay, for the quantifier is for random PIs and BIs. This holds. Yeah. So for random P with high probability over the choice of PI and BI, for every F, there exists A1 to AM. Yeah. This any questions? Okay. So now all we need to do is prove this fact. So yeah, so let's suppose there's a polynomial f that equals the summation of AI times Pi minus Bi. So we write out every monomial. This looks a bit scary, but it's actually not. It's just writing out the monomials on both sides. where the monomials are indexed by alpha. Alpha is a multi-set. Anyway, let's just compare the coefficients on both sides. We get a linear system that looks like this. So so what we need is that for any f hat, because remember f hat are the coefficients of f. So for any f hat, there exists a hat such that this holds. That's all we need. And this basically means that this matrix M has to be full row rank. It's a fat matrix, and the columns span everything. Yeah, and column spanning everything means that rows are linearly independent. Okay. So a priori, it's kind of hard to analyze whether this M is full rank or not. But we observe that this random matrix has some special structure, and so our strategy is to find submatrices such that each submatrix is full rank. They cover all the rows of M, and they have disjoint columns. And finally, the diagonal entries of each submatrix are independent of the off-diagonal entries and the other submatrices. So this seems a little bit weird at first. Hopefully later it'll become clear why the fourth thing is needed. So the idea is to extract these submatrices from the matrix M and somehow stitch these submatrices together to prove that M is full rank. And yeah, this is like a little bit vague for now, but hopefully then the next slide will clear things up a bit. Okay. So this is the main lemma that stitches like matrices together. So suppose M has this block matrix structure, and A is full rank. B is this B prime plus G times identity. So basically, this diagonal of B is random and independent of the rest. Yeah, G is Gaussian independent of the rest. Then M is full rank, and this is pretty easy to see. Why? Yeah, this is how we stitch things together.
Hey, Tim.
Because M is full rank if and only if the shared complement is full rank. So this thing. But suppose it's not full rank, then that means this matrix has to be this matrix is low rank, which means G has to be an eigenvalue of this. But because this matrix has like finitely many eigenvalues, the probability that G, an independent sample from Gaussian, like coincides with these finitely many numbers is 0. Yeah, so this is why we need this, we need this fourth condition. Okay, and 3 minutes. So a remark, our upper bound actually holds for any nice distribution. So it's not just Gaussian, can be any continuous distribution or any like discrete distribution that has some proper anti-concentration property. As long as this is like low probability, we're good. Okay, and I will actually stop here. I won't go into the details of the matrix M because I think the rest of the talk is more interesting than that. So yeah, so but basically the rest is just to actually look at the matrix M and look at the structure of the matrix and find a clever way to extract these submatrices that satisfy this.
Anupam asks if you can recap what M is.
Oh no, yes. So this matrix M is, I didn't write it here because I don't think it's helpful for the audience. It's like once you compare these monomials, you write M, you can write it out, and we don't need to remember for the rest of the talk. Yeah, Anupam asked whether we should remember what M is for the rest of the talk. We don't, because I'm going to jump to the lower bounds next. Yeah. Okay. Yeah, it went really fast, and this is Anupam's question. Yeah, so yeah, I decided to cut like not explain what matrix M is because I think it's a bit complicated and I want to spend time on lower bounds. So
Just like how we finish on that, right?
yeah. Yes. Okay. Okay, so a recap. We proved that degree D SOS, actually degree D no standard sauce, succeeds when M is greater than order n squared over D. And we proved this by proving this complete generated ideal is complete. And yeah, we do so by proving that M is 4 row rank. And it's a final remark that it's pretty crucial in our analysis that the P1 to PM are dense. Because, for example, suppose each PR is actually just a single monomial where the indices I1 and I2 are chosen randomly. So they're sparse in the monomial basis. Then we actually need or we can construct examples where we need n squared over 2 for the completeness to hold. So this is like one key point that's different from the usual CSP refutation, where the each predicate is only on a small number of variables. So in their case, the polynomial is sparse. Okay. Yeah, if it's sparse, then at least in this example, you can prove that n squared over 2 is needed. Yeah. Okay, so yeah, I want to go to the lower bound. Okay, so yeah, a bit of background on the low degree polynomial method. This is mostly from these surveys, Sam Hopkins' thesis and this paper from Kaminsky, Wine, and Bandera. Okay, so consider the hypothesis testing problem of distinguishing two distributions, a null distribution and a planted distribution over R to the K for some K. This is an example. The null distribution is just an Erdős-Rényi graph G and half. And the planted distribution is G and half plus a clique of size root n, where this clique is chosen at a random location. And so usually we call the second distribution the planted distribution because we plant something in the distribution. Like in this case, we plant a large clique in a random graph. That's why it's called planted distribution. And also I use this example is because the low degree hardness framework is actually arises from the studying the planted clique problem. Okay. And we say that a testing algorithm is a function from R to K to R on input Z. And it outputs planted if TK Z exceeds some threshold tau. Okay. So there's a classical lemma from Neyman Pearson, which shows that the optimal test is the likelihood ratio test. And this optimal is in some sense in statistics. But so the problem is that this likelihood ratio test is usually very hard to compute given an input. If it's usually in average case problems, this is impossible to compute, or rather we don't know how to compute it. So we restrict to test functions that are low degree polynomials of the input. So let's consider the following optimization problem. We're maximizing over the expected f under the planted distribution such that f is properly normalized. So the expected f squared under the null equals 1. And f is a degree D polynomial. So you see that if f is like roughly 1 under the null distribution, but the expected f under the planted is very large, then it's kind of like you can see there can be a distinguishing polynomial f. Okay, and so previous work have proved that this optimizer is the normalized truncated likelihood ratio, and the optimum value is this. So I'm not going to go into detail of this, but it suffices to prove that this quantity, which is the sum over its expected chi alpha to squared, and this expectation is over the planted distribution, is less than 1. And this is basically saying that this optimization problem, the value of it is constant. And when it's constant, you can see that the best polynomial is it's hard to distinguish between the null and planted because the value of f is quite close to each other. Yeah. Okay. And here, chi alpha is the basis under the null distribution, and we're going to use Hermite basis because our input is Gaussian. Okay, so this is a little bit. If this is hard to follow, it's okay because usually the main step in this low degree hardness framework is to find a planted distribution that's hard to distinguish. So once you have a planted distribution and you think that is hard to distinguish, you follow these steps and calculate this quantity and say that it's smaller than 1, and you're done. So in our work and also many previous works, really the creativity is to find a planted distribution that's hard to distinguish.
So is there any idea how the function f looks like, which is the optimal?
Yeah. So the optimal is this is L truncated likelihood ratio. So it's basically, yeah, I can explain in more detail. Basically, you choose a basis for under the null distribution, and you write the low degree part of the likelihood ratio function. Yeah. Okay. So you might ask, what is the low degree polynomials too restricted? So it turns out that order log n degree polynomials can simulate many algorithms such as power iteration. So it can compute spectral norms, approximate message passing, local algorithms, etc. So they actually capture the best known algorithms for many canonical problems, like tensor PCA or planet clique, etc. And recently, it's proven that under appropriate assumptions, order log n degree polynomials are as powerful as the SQ model, which is another class of computation model, which I will explain. And more importantly, there's a connection to SOS. There's a conjecture that indistinguishability by degree D polynomials implies lower bounds for order D degree SOS. So there's this is called the pseudo calibration conjecture. It's a pretty famous conjecture. Yeah, and so the reason people look at this is because first of all, in average case problems, it's kind of impossible to prove NP hardness. So researchers use more restricted hardness results to have an idea of some algorithmic threshold. So this low degree framework has been used in many other previous works. Okay, so now let's come back to our problem. So we need to define a planted distribution that's hard to distinguish from our random polynomial system. Let's first fix the parameter C that's small enough. We sample Z from the normalized Boolean cube uniformly. And for each I, we sample BI to be Gaussian. And then for each GI, we sample it from, GI is the Gaussian matrix, condition on this GI dot ZZ transpose equals C times BI. And then we set PI to be X transpose GI X. And when I say sample G condition on G dot B equals B, where V is a unit vector, I mean that first sample an H from the Gaussian vector, and then set G to be this. And it's pretty easy to check that V is a unit vector and G dot V equals B. Yeah. Okay, so yeah, so this is what I mean when I say sample Gaussian's condition on this. Yeah.
Can you give
This is the lower bound for low degree polynomials. In the, we want to say that low degree polynomials fail at refuting our random system.
So low degree polynomials is the
Or rather, like, so think of an algorithm to be any low degree function of the input. And we say that if the input is it's a thresholded function, basically. Yeah, and we want to say that if this function exceeds some threshold, when the input is this planted distribution, like given an input, if it exceeds some threshold, then we output planted. Otherwise, we output null. And we want to show that any low degree polynomials cannot distinguish these two. Yeah. Any other questions? Everything clear? Okay, some remarks on the planted distribution. So first of all, it's always feasible. The feasible solution is Z over root C. It's pretty easy to see from the definition. And this is different from the natural planted distribution. And now I'll tell you what the natural planted distribution is. It's natural because it's probably the first distribution you'll think about when you encounter this problem. So first you sample X star, and you sample PI uniformly with uniformly random coefficients. And then you set the right-hand side BI to be PI of X star. Yeah, this is pretty natural. Turns out this is actually easy to distinguish from the random polynomial system. And the X star can be recovered roughly at the info theoretic threshold. So it's easy to distinguish, so it doesn't work for our lower bound.
Did you mean BIs are Gaussian coefficients or uniform?
Oh yeah, think of them as Gaussian. Yeah. If you first sample the PIs and then set the BIs, then you don't get anything. Or rather, our lower bound doesn't work. Yeah. So yeah, it's.
Can you describe a little bit about what algorithm covers X star again?
Oh, I think it's some like nuclear norm optimization thing, which I'm not too sure. Yeah, basically, like I think solving some SDP will find it. Yeah.
So you could point out that this is the matrix sensing problem. Like this distribution is simply the matrix sensing problem. It has no efficient algorithm.
Right. Yeah. Okay. Yeah. So basically, like instead of choosing the PIs first and then setting the BIs, we first choose the right-hand side BIs first, and then choose the coefficients of PI to be mildly correlated. Yeah. And this, the hope is that low degree polynomials don't capture this mild correlation. Okay, and another remark is that the norm of the planted solution, which is this X star, is 1 over root C. And C, we set it to be some small number. And this is actually important because, or it's necessary because there's an efficient distinguisher if C is too large. And this, the distinguisher is the norm of this matrix. It's not too important, but basically all I want to say is that if C is too large, there is an easy distinguisher. So, okay. So remember, we want to prove that the variance of this is smaller than 1, and this is some scary summation. And I want to give a brief sketch of this. And so for simplicity, I want to assume BI equals 0 because it's like it captures most of the main ideas. And so now we're given input G1 to Gm, where Z transpose Gi Z equals 0, and Z is our planted solution. And we want to analyze this quantity. And here, alpha is an index of the Hermite polynomial, which is m times n times m. N, sorry, yeah. So we view alpha as a label-directed multi-graph. So such that self-loops are allowed, and this graph has n vertices, alpha edges, and this notation just means the sum over all entries in alpha. and each edge has a label from M. Okay. So, and we also denote alpha 1 to alpha M to be, like we view each alpha S as the adjacency matrix of the subgraph where the edges have label S. Clear? And we denote delta to be the degree of this graph. This is just sum over the in degree and out degree. So delta I is the total degree of vertex I in this multigraph. And then here's the lemma that we proved. So this is this quantity is not important. The important thing is that this is only non-zero when delta I is even, and this every label appears even number of times. That's the important part. So it's actually this. So this calculation really reduces to some like interesting combinatorial problems. So let's say we first fix the number of edges to be E, and E has to be smaller than D. So how many directed graphs with n vertices, E edges, and have even degrees? So the answer is less than 8n to the E. And I'm sure like for Jeff, for example, can improve that 8 by some constant factors. And how many ways can you assign labels in M such that each label appears even number of times? And we assign labels to the edges of the graph. So the answer is that it's dominated by the case when each label appears twice. And this is bounded by this 2me to the E over 2. So you see that like that scary looking summation before really reduces to some simple combinatorial problems that we might see like in homeworks, right? So and I'm sure these constants can be optimized, but we don't really care about constants here. So when M is order n squared over D, that scary looking summation becomes this summation. And we can see that when M is smaller than some constant times n squared over D, we get this to be less than 1. So that's the end of the proof sketch. Are there any questions? Yeah.
Can you refresh on what this variance of L is again?
Yeah. So that. Oh, I think there's a recap here. Yeah. So it's really in the. Sorry. Let's go back to the background. Sorry. Yeah, so basically we wanted to show that this optimization problem's value is quite small. Yeah, and by some calculations, it's not too hard. The calculations, we can see that this really comes down to proving this. Yeah. Okay. Okay, just a recap. So we showed that degree D polynomials fail when M is less than n squared over D. And by fail, we mean that it fails to distinguish the null distribution, which is our random system, and the planted distribution. Yeah, and we construct a hard planted distribution. Right, fails to distinguish between these. And the failure to distinguish these two implies the failure to refute our random polynomial system. Okay, so that's the end of the low degree hardness. And I have like 7 minutes. Okay. Yeah. So I want to talk a little bit about degree 2 SOS because I think it's quite interesting. So we want to prove a degree 2 SOS lower bound here. Well, yeah, basically we want to show it at what M does degree 2 SOS fail. So what is degree 2 SOS? Okay, here we assume BI equals 0. So degree 2 SOS is actually just this simple semi-definite program. Here we're solving for x, where x is the PSD. And the trace of GIX, this actually just means like GI dot x equals 0 for all I. So notice that x equals 0 is always a solution. but we want some non-trivial solution. Okay, so now observe that the trace of GIX equals 0 defines a random linear subspace K of dimension this minus M. Here, this is just a dimension of the space of symmetric matrices. Okay. And let's C be the PSD cone. So our question is, does the PSD cone intersect K non-trivially? And what if it's the intersection trivial? Trivial just means that the intersection is 0, only 0. If it's only 0, then this STP is infeasible. I guess the only solution is 0. Then this means that degree 2 SO succeeds at refuting. Right. On the other hand, if there's some non-trivial solution, that means that this degree 2 SO thinks this system is feasible. So yeah, does this make sense? Yeah, so what is so remember that our linear subspace K is a random random subspace. So the question is, what is this probability where Q is the random rotation and K is a fixed linear subspace of a certain dimension? So this is a question in conic geometry. This is why I think this section is pretty cool and I want to talk about it. Here's a lemma from some authors who work in conic geometry. Let's C and K be convex cones, and I think they actually work in like matrix sensing and stuff. Yeah. Anyway, I don't remember. Yeah. Okay. Yeah. Let's C and K be convex cones in R to the n, big N, and let Q be a random rotation matrix. Then the probability, this probability is governed by this delta C plus delta K. Delta is a statistical dimension, and the exact definition is not important here. It's really just generalization of dimension. So for any linear subspace, we know its dimension, right? So this is just a generalization of dimension to convex cones. Yeah. So you see here's actually a phase transition here. If the sum of the dimension is smaller than n, roughly n, then the probability of this being this not equal 0 is quite small. But if it's slightly larger, then it's almost 1. So there's a phase transition here. And yeah, it's actually very important. Like people study this because it arises in some phase transition in other like stat ML type problems. Okay, and I'm not going to define this, but for K, which is a linear subspace, it's just a dimension. So it's this quantity. And for the convex cone, delta C is this 1/4 times n plus 1. Okay, so like we just plug that in. Yeah, we plug in, and we see that when m is larger than n squared over 4, the SDP is infeasible with high probability. That means that degree 2 SOS succeeds at refuting. And on the other hand, if it's slightly smaller, then this SDP is feasible, which means degree 2 SOS fails. It thinks that there is a feasible solution. Okay, so this suggests that n squared over 4 is the threshold for degree 2. Yeah, and I think I just wanted. I think this is interesting because it's like using conic geometry to prove SOS. Like it's like quite different than the existing work on SOS, like both upper and lower bounds. So something cute that I want to talk about in the talk. Yeah. So I think this is the end of the talk. Conclusion. For random quadratic polynomials, this seems to be the correct algorithmic threshold for n to the O of d runtime. And we prove the upper bound, which is degree d no science actually, and lower bound is in the degree D low degree harness framework. And yeah, like I said, everything I've said so far is for quadratic polynomials. We also prove it for degree capital D polynomials, and this is the threshold. So that's it. Thank you.